All right, 11:10. Good morning, guys. Today we're gonna do a recitation on supervised learning. Please goes to this whiteboard, Jetboard, or Jamboard on Google, so I can share some notes. So, yeah, how can I? Okay, can you guys see the share screen that is the whiteboard right now?
Yeah.
Okay. Okay, because I have multiple screens, and then I just noticed that last week I always share on a wrong desktop. So it's actually nothing. All right, so now we have this chatbot, and then I'm writing on my iPad. Okay, so supervised learning. We're gonna do an example on LMS and on a naive base. Hopefully, you know how exactly this works. After. So let's see. Okay, first of all, for the assignment, you as Wheeler mentioned, you have to like training a classifier for each hypothesis. Hypothesis means for each digit. You know, for digit 0, you training a model for that, and then you know your output, your y would be you know, and 0 and 1. So if it's a linear model, then you know you have this y equal theta 0 plus theta 1 x1 plus theta 2 x2 plus theta 3 x3, etc. So this is kind of one of the hypotheses you want to learn for digit 1, you know, for handwritten digit 1, right? And then you want to train another hypothesis, you know, another same, you know, whatever formula for LS for digit 2, and then you do the same thing for digit 3 until for digit 9. I guess there's one for digit 0 as well. 0. Yeah. Same thing for digit 1. So you have to train 10 hypotheses, 10 formula for each digit. And then in the end, you will have this prediction, you know, those features, you know, this axis for the assignment is actually the value for each pixel, right? For each pixel, there's a value, you know, 0 to 5. And then those are your axis, X value, those are your feature value. And then given a new image, you know, somebody write something like, and then you're gonna predict, okay, what is this digit? What is this number? And then you're reading all the pixels, you know, reading all the pixels values for this, and then putting into this 10 of formula, and then to predict the y's. you know, your prediction. So you feed this back into all this trend hypothesis, and then you're gonna have this y values. So what you trend actually is this hypothesis, which means this formula. Actually, it's this thetas, right? This all of this coefficient for your features. That's what you want to compute in the end after the training. So you have the model, you feed in the x from the digits, and then you predict your y. So you have a y, you know, this is 0.8, this is 0.74, etc. And then you have 10 values in between 1 and 10. And then you normalize it and then find that the largest one. So you sum them up, you know, sum all y's. And then for each y, you put there. And then your prediction, okay, this is a number 4. So there's a 4 here. It's a 4 here. Right? Oh no, this value for number 4 is, you know, 0.9. Then your prediction would be, you know, this is 0.9. Then your prediction for this image would be, okay, it's a 4. All right, this is very high level, how you're gonna do this. And then we're gonna do an example on how to train this hypothesis. All right, everybody kind of clear? So for naive Bayes, it's the same. You're gonna have some predictions on the y's, and then have a normalized value, and then pick the best normalized value as your prediction. So we're also gonna do an example, but not on the digit example. All right. So, oh, Connor has a question. So since we're dealing with 200 values, we'll have 201 theta values. Yes, yes, one for each pixel, and then you have this y intersection or whatever the one is here. So this is the 201. So this one. So you will have 200 values, and then this one y intersections, I would say, because if you, yeah, anyway. Plus what? Yes. How many pixels you have plus 1 is your feature number. Okay. Any other questions? Actually, there are only 106 values, 14 by 14 images. Okay, yeah. So you have to train 197 thetas, you know, 197 coefficient for your LMS.
What's the confidence we're asked to output?
So yeah, this is the confidence, the left bottom side. So, okay, yeah.
Okay, so whatever that normalized.
Yeah, normalize the value in between 0 and 1. So that's your confidence. So, you know, if and two y's have a 0.5 and 0.5, and then your confidence would be 50-50 because they have the, you know, if they have the same predicted value. And then you say, okay, I don't have very good confidence on each of those. You know, 50-50, they have this quite similar values.
So what is the confidence? Is it y divided by that?
By the summation of all, sorry, that's all. That's all y's. Right? You sum up all the predicted values of your hypothesis, and then that's the denominator, and then the numerator is the value, each of them. and then you pick the one has the largest confidence.
So that's almost never going to be near 1 unless everything fires a 0 except for the one thing that
Yes.
fires like a 1.
Yes, yes.
Okay.
Yeah, correct. And then for k nearest neighbor, it is I think you will have to confidence. All right, let's talk about confidence. So for k nearest neighbor, I think you select the k nearest one, and then you will pick the majority of the k nearest one. Say, okay, all of the neighbor of this image, and the 5 nearest one, it could be 4, 4, 4, 4, 9, right? You pick the 5 nearest neighbor, and then okay, your best hypothesis is 4, so that's 4 here. So your confidence for this one is 4 over 5. Make sense? Okay. And yeah, that's then for and naive Bayes, that's equal summation of all y's over y. Okay.
What is the word above K, like in the K and N? What is that word?
That's the k nearest. That's the k number you select. Like if
Okay.
your parameter is 5, then the k is 5, right? And then the majority is the most frequent one among your neighbors, among your k nearest neighbors.
So for K and N, are we not doing 10 different classifiers?
Yeah, for KN it's pretty similar because you have to going through all the training data. So yeah, given an image, so like 4, and then you have all the digits on this, and then for each digits you compute the distance with each of these the input value, input training data, and then it's a mean square distance, whatever. It's a high dimensional Euclidean distance for each of the pixel is 1 dimension, and then you computed the distance between this input value and then all the training data. So you have this for loop all through all the training data, and then you pick the closest 5.
Okay, thank you.
Yeah. So that should be pretty simple, but you're gonna kind of see it's very slow and then a lot of memory intensive because you have to loading all the data into your memory. So that's why it's not very practical in real world problems.
You are showing a wrong slide.
Oh, all right. Here. All right, this thing doesn't synchronize very well. Okay, let's move on to one example of the least mean square approach. Say we want to train this model of say y equal 2x. Oh, maybe I want to write it the other way so we be consistent. Y equals 3 plus 2x. All right, so we don't know what this is. So what actually we want to learn is a model like y equals theta 0 plus theta 1x. All right, and then say we have a bunch of data reading. So we know that we have a data, y1 equals 7, x1 equal 2, 1 input data, y2 equal 19, 19, and x1, x2 equal 8. Does that fit the model? 2 times 8 is 16 plus 3 is 19. Okay, yeah, that's correct. So y3 equal 11, the x3 equal 4, right? So we have 3 data, and then we want to learn this model. Basically, we want to learn what's the value of theta 0 and then theta 1 is. And then the ground truth is theta 0 equals 3, theta 1 equal 2. All right. And then we are updating, we're doing this online. So we update our theta 0 and then theta 1, read the data by data, data point by data point. And then by this update rule, which is theta, update theta by going the gradient descent, which is finding the difference between the hypothesis value and the data value. And then for each feature, we training a theta, right? Then we have alpha equal 0.1. So here in this example, we're using fixed learning rate, which is 0.01. So, okay, that's good. Let's go. Go with this. So for initially theta 0, let's see if it is fitting this. Initially theta 0 equals 0, theta 1 equals 0, right? And then we compute, so for the first data is y1 equals 7, x1 equal 2. Then we want to compute our y hat. So y hat is equal theta 0 plus theta 1 plus x, which is 0 plus 0 times 2, x equal 2, which is 0, right? And then we're starting to update theta 0. Theta 0 is equal theta 0 minus alpha times y hat minus y, the differences. Then times, there's no x. X is actually 1 here for theta 0. So this is 1 times 1. So this is equal 0 minus 0.01, which is, so it's y hat minus y. Y hat is 0. Y is 7. Which is 0.07. So that's updated theta by reading in one data point. And then we update theta 1. So for you guys, you have to update whatever 197 thetas. So theta 1 minus alpha y hat minus yx. So that is theta 1 before it's 0 right now. And then it's 0 minus 7 times 2, which is equal 0.14. All right, after reading one data point, theta 0 should become 0.07, and then theta 1 should become 0.14. Then we read the second data point. So it goes to a new page.
I have a question with the
question.
page real quick. So where does that 1 and the x, is it x for every theta after, if we have more thetas, would that x term be x for all of them?
No, so each one is for each feature, right?
Okay.
Are you talking about this one?
Yeah.
So this one is the one here. Do you see that? Okay, see my mouth?
Yep.
Okay, so the one here, it's the, yeah, I forgot what Wheeler called this term is, yeah, I would
Bias
like,
term?
what?
The bias term?
Yeah, the bias term, yes. It's for the bias term, X is always 1. So you want to add in all your features plus the bias term. So the bias term, the X is 1. So this is this 1 here. All right. So maybe we want to be consistent and then put a times 1 here. Okay. Times 1. All right. So let's doing update on the second data point, which is what is it? It's y equal 19. Equal 19, and then x equal whatever 8. X equal 8. So first we compute the y hat. That is theta 0 plus theta 1 times x, which is 0.07. So notice that the theta 0, the previous update theta 0 to 0.07. So theta 0 is 0.07, and plus theta 1 is 0.14 times the x is 8. So the hypothesis is, right now the hypothesis is 1.19. And then we update our thetas based on the difference on the current y hat value and then the actual data point y, which is theta 0 equals theta 0 minus alpha, the difference between the hypothesis value and then the actual data value. So I omitted the 1 here since it's the bias term. 0.7 minus 0.1 times 1.119 minus 19. So it's a large difference so far. This is 0.07 minus, so I already have this, so I just have to put it on 0.1781. So that is 0.2481. And then for theta 1, doing the same thing, but right now this is actually feature. So minus alpha y hat minus y and times x, which is equal 0.14. One more 0, that's wrong. Times 1 minus 19 times 8. So this gives us 1.56 and 48. Right? After the second update, theta 1 becomes 0.2481. So I think it's getting closer to 3. All right, so that's getting closer to 3 as we can see. And then theta 1 becomes 1.5648. And then, yeah, before it is 0.14, so it's getting closer to 2. Right? Then we do the same thing for the third update. That is y equal 11, x equal 4. So y hat equal theta 0 plus theta 1x. So that's 2481 plus 5648 times 4. That is 6.507. And theta 0. What the heck? What happens? Why I can't write here? Theta 0 equal. So yeah, I guess you got the idea. So this one should be updated to 0.293, and then 0 theta 1 becomes 1.744. All right. So you're gonna reading all the training data like this. This is only 3 training data, but if you have multiple images you can reading, whether it's 500 or 10,000. So read them all, and then in the end you will have your updated hypothesis. All right, cool. Everybody understand? So okay, I see D Park have a problem. Isn't x equal 2 for first iteration? Should theta?
No, I got it.
Oh, we got it. We got it. Okay. Okay.
Explained it. Yep. Thank you.
Nice. Okay. Any other questions about LMS? Okay. All right. For graduate students, we have to implement a naive Bayes. Let's see how that works. I think we'll go over that really quick. That may be too quick for him. Hopefully, we have 20 minutes to doing this. So we're gonna, let's see, using this Bayesian law. All right. So we're gonna using this Bayesian law, which is the probability of, and given the data, what is the true hypothesis is. The probability of that. So given all of the images, all of the training data, all of the training images you have, is it 7? Is it 7 or is it 4? So this is the probability we want to get in the end. All right. Given the data, what is the true hypothesis is? That would equal the probability of the hypothesis itself. How often a 7 is in all the training data. How many 7s you have in your training images. The frequent of hypothesis. And given the hypothesis, what is the data? If we know it is a 7, what is the data is later on. So we're gonna work on this using the naive assumption, right? Using the naive assumption by saying that, okay, I know this is a 7. What is the probability of that pixel being a dark pixel or being a white pixel? And then we multiply them together. So all right, I will explain that later. And then this is divided by the probability of a data. So things we're gonna test on all hypotheses. We're gonna test it on all hypotheses. So this term doesn't matter because this is gonna be the same for all hypotheses. So basically, normally people would using this as an whatever alpha is. So this is not a learning rate anymore. It's just a coefficient of P of H. And then this is a positive number. So non-zero number. So we can omit it. It's gonna be proportional to, yeah, maybe I shouldn't using the alpha. Anyway, so this is not alpha anymore. This is proportional to this value. Right? This is what we care to compute. And then how we compute this. So we compute this by the naive assumption, which means, so the first term is really simple, right? So you just count. So basically for naive Bayes, what you do is you're reading the image and then you count. So here, the one is you count you count for all the hypotheses. You know, you're reading all the images. If you have 1,000 images, and then for this term you have you know, 57, and then you say, okay, the hypothesis of a 7 is you know, 50 over 100. So you count how many hypotheses you have seen in among all your data. And then this term, we're gonna using the naive law or naive assumption. So the, so the probability of naive law is the probability of each pixel. So and then xi is the value of that given that hypothesis. All right. So given the data means given the hypothesis, what's the probability of that digit of that data with which means of that image we get, right? And then we count the probability of all the pixel values all right? So does that kind of make sense? So you have a pixel value, whatever 7 is, and then for each pixel, so you say, okay, have all the image of 7s, I have them, and then I starting to count. You know, I starting to count. Okay, what's the probability of this pixel being 1? What's the probability of this pixel being, you know, 5, dark? 1, I think 1 is white, and then 5 is dark. I don't know. I don't remember. Anyway, so you get this by still counting, but counting on the pixels. All right, and then later on you have all this, then you can just plug them back in to get this. What do you want to compute? All right. So I'm not gonna do an example on the pixel problem because that's your job. So I'm gonna do an example on the book, which is a tennis play. It wants to predict whether it's a good day to play tennis or not. Okay, let's see. I have take some images. Okay, so we have this data. So if it's a sunny day and the temperature is hot, if the humidity is high, it's a very wet. And then if it's a weak wind, we don't want to play tennis. Otherwise, if it's it's an overcast day and then it's hot, and then it's humidity is high, and then it's weak, we do want to play tennis. All right, and then if it's a sunny day and the temperature is cool and then humidity is normal and then the wind is weak, we do want to play tennis. So etc. So then given measurements of all the features, all the, if it's what's the outlook, what's the temperature, what's the humidity, what's the wind, given a new data point, 15, and then it can be each of this either sunny or overcast already, each of these values. And then we want to predict whether we want to play tennis or not, right? Everyone clear with the problem? So we want to using naive Bayes to solve this, all right? So basically, we starting to counting by reading in the input, value. So, okay, this is what we're gonna do. select another files to, yeah, I don't want to write this down many times. So first of all, we have to count. Okay, let's make some red pens here. So here, first of all, we have to count the hypothesis. How many yes, how many no? So if we look at this, all the reds are yes, a good days to play tennis, and then all the darks or the black are no's. So we have 1, 2, 3, 4 over 14. Oh, it's 5. Oh, 5, yeah, this one. 1, 2, 3, 4, 5. 5, no play. So no play, there's a 5 over 14, and then there's a 9 over 14 of yes. This is the hypothesis. This is this term, right? PH, probability of hypothesis. We got it. And then we compute by the naive base, by the naive assumption. We want to compute for each feature in the data, what is the hypothesis, given the hypothesis, what is the feature value? What's the probability of being that feature value? So given yes, what is the probability of the outlook is sunny, right? And then we starting to count, you know, there's a 9 yes, you know, all the reds, there's 9 of yes, 1, 2, 3, 4, 5, 6, 7, 8, 9 yes. And then how many sunny we have? We look at the outlook, and then there's 1 sunny, there's 2 sunny. So there's 2 sunnies. So the value of given play tennis, yes. And then the feature value is sunny for outlook. The probability of that is 2 over 9, right? And then remember that Wheeler mentioned we have to do this +1 smoothing. +1 smoothing. Otherwise, if you have a 0, it's gonna, you know, make everything 0. So that's not good. It's not fair. So we +1 to this value, +1 to this value, which would be equal 3 over 12. Right? I think that's right. Or we +1. I think we +1 on the data point instead of +1 on here. So yeah, I'm wrong. So it's 3 over 9. Okay. Wait. So I think do we +1 on the numerator or the whole value? I think we +1 on the numerator. So it becomes 3. Oh yeah, so yeah, I guess I'm right. So we +1 here, and this becomes 12 because we +3. Wait, how this work? Oh yeah, because I think for each data value, we want to +1. So we assume we have seen rainy once in yes, and then we have seen rainy once in no. All right. And we assume we have seen overcast once in yes, overcast 1 in no. So for all the yes, is how many of there's a sunny, overcast, rainy. Yeah, there's a 3 type of values we could see: sunny, overcast, rainy. So for each one we add 3. And then so for actually, so this is gonna be, so can I zoom this? Yeah. Let's erase this. Maybe I want to do it on the pad. So this +1 is very important, otherwise your training results gonna be worse. And reload. It's stuck on my dismiss. Okay. So can I just, yeah. All right, fantastic. So this will be equal 2 + 1 over 9 + 3. Because we assume each data value have been seen once in the yes. So 9 + 3. And then we have seen y once the if the counter here is 0, then it's gonna be 0 + 1. So counter here is 2, so 2 + 1 is 3. All right. Everybody got this? All the graduate students, please. Okay. So then the same thing, we counter how many overcasts we see in yes. So that's 1, 2, 3, 4. 4 overcasts we see in yes. And then we using the +1 smooth, so we see it 5 times over 12. And then we do the same thing. We counter for all the values for all the yes, and then we counter for all the values for all the no's. And then we do the same thing for the second feature, which is temperature. So how many hot we see in yes? So in yes, hot is 1, 2. 2 hot in yes. So it's 2 over 9. Because it's 9 yes, 2 over 9, and then doing +1 smooth, so 3 over 12. All right, and let me upload. So then we do for the rest of the 2 feature. For the humanity and the wind, we got all the data. Then later on, we have this data input. Just outlook is sunny, temperature is cool, humidity is high, wind is strong. Should we play tennis or not? Then we plug in this into 2 hypotheses, right? The first hypothesis is yes, and then we plug back into this formula. We plug in back into this formula. So the hypothesis of yes, that is 9 over 14. And then the probability of given the hypothesis yes, what's the data is, what's the current input we have. And then we're gonna using naive way, which is okay, given yes, what is the probability of sunny? Since we already count that, we would have that value. Given yes, what is probability of cool? Given yes, what is the probability of humidity high? Given yes, what is the probability of wind is strong? And then multiply them together, and then multiply them by the probability of the hypothesis. We got 0.0053 by computing this data. And then we test this on another hypothesis. No, do not play tennis. And then reading all the counter data, all the probabilities, we got a 0.0206. That is higher than the probability of hypothesis yes. So the prediction is no. Given this weather condition, we don't want to play tennis. All right, everybody got this? So then the confidence for this gonna be you plus these two values together, and then divide the hypothesis, which is 0.0206 over the summation. So normalize the prediction value is your confidence. So how confident you're to saying no, it's not a good weather. All right. So that is our example on the naive Bayes. Do people understand? Any questions?
We have questions in the chat.
Okay, so I'm not really clear on whether that 3 is coming from in the denominator. You're adding 1 smoothing. Yeah, adding 1 means adding 1 to each possible values. So see how many values we have here for sunny. We have sunny, which is 1, overcast, 2, rain, 3. We have 3 possible values for this feature, right? So for each of them, we have to add 1. Assume we have seen them once in each of the hypotheses. So for yes, if we never see sunny, we still have to add 1 to the sunny for the yes, right? For no, if we never see, overcast, we still have to add 1 to that no. Otherwise, the naive way, after it's multiplied together, this term gonna be 0, which is too bad. So basically, for you, for pixel 1, and if I see whatever, yeah. So let's draw. So, how can I redo this? Yeah, so I just want to zoom down, 9 plus 3. So, okay, let's see, and then using mouse. Okay, that's better. For you, that you have pixels, then for this pixel, maybe you see all the zeros for this pixel, but for value 1, for value 2, for value 3, for value 4, for value 5, you have to assume you see them once, for hypothesis 7. Do you know what I mean? Kana? Okay, yeah, so that's plus 1. So we plus 3 here in this denominator. We plus 3 here. Oh, sorry, I'm not in there. So we plus 3 here in this denominator because there's 3 possible values. And then plus 1, this is actually plus 1 happens because if this is 0, then it's going to be 0. Otherwise, this time it's not 0. So, okay, cool. That's how plus 1 smoothing work. And, yeah, that's pretty much what I'm going to say today. It does it for me. And good luck on the implementations, guys. Yeah, if you have any more questions, shout it out. Otherwise, post, and if you later on have questions, post it on Piazza. We were gonna try to help you. All right. Cool. Bye, guys. Have a nice weekend.